Hi everyone, welcome to this first lab. So in this lab I will show you how you can run your very first quantum algorithms on actual quantum computers. So let me share my screen so you can just follow whatever I'm doing. So you just start by going to quantum-computing.ibm.com, and then, well, if you haven't done an account, created an account yet, you need to first create an account, but this should take like a minute at most. And well, then you can log in. And what we want to do is we want to launch the lab. If you're actually using it for the very first time, you might also want to launch Quantum Composer, where you can just drag and drop some gates and you don't need any programming at all. However, we're not going into detail for that now. You can just play around with that if you want to. I will now go with you through an example of the Deutsch-Jozsa algorithm, and then afterwards also an example of the Rovers algorithm. And see how you can then run this both using the simulator or using one of IBM's actual quantum devices. So we'll start with, well, some imports that we need to do. Well, we import NumPy, we import the IBM Q, for simulating everything, for creating and executing quantum circuits, and also we need to load our account. And of course, plotting the histogram later, we will need that. So this is all just some imports, and just copy paste those in theory. Then we will create a function. The function we call Deutsch-Jozsa oracle. And we give it two variables. One is the case. So with the case, I mean we can specify whether we want it to be balanced or constant. And then n, which should be the number of qubits that we're using. So this is our function, and we have these two variables. Now let's see. First, we need to create a quantum circuit. Very first thing. The quantum circuit we call Oracle QC, and we actually create one not only on n qubits, but on n+1 qubits. And the reason we're choosing n+1 qubits is maybe you remember from the first lecture, or the second lecture, the one on where we learned about Deutsch-Jozsa's algorithm, that you need for the phase oracle, you actually need this extra auxiliary qubit on which the one that is in the minus state initially, and that is also output then later in the minus state. And we don't really we just consider something as a phase oracle, but for the phase oracle, in theory, we always need this extra qubit. So that's why we have n+1 qubits. Then let us make here define into the balance case and the constant case, and depending on that, how the oracle looks like. So for the balance case, that is the case where for half of the inputs we will get 0, and for half of the outputs we will get 1. There's actually a lot of different ways of how we can implement that. I mean, the easiest, I guess, the most trivial one would be we just choose one qubit out of all the input qubits and say if this qubit is 0, we output 0. If this qubit is 1, we output 1. Thereby, half of the cases will be 0, half of the cases will be 1. Very trivial case. I chose a slightly more difficult one, but okay. Still a very easy one, where I'm just doing a for loop over all the first n qubits, and I apply a CNOT gate to the last qubit. So here you should note that if I do range n, it actually starts with 0 and it goes until n-1. So my first n qubits will be qubits 0 to n-1. And each of those, qubit is my index through which I go through, I apply, controlled on that, I apply a CNOT gate on my nth, so on the last qubit. Which means that if we now have CNOT gates applied to every single qubit, we basically in the end just take the parity. So each time where the control qubit is 1, we flip the qubit by 1, we flip the qubit, so in the end we're taking the parity and calculate that on the last qubit. Okay, so then if the case is constant, then, however, we basically don't need to do anything. But okay, in theory, let's do it as we learned it in the theoretical part. We have a random number because it could be constantly 0 or it could be constantly 1. If it is constantly 0, then we just output 1 every single time. Yeah, then we output. If it is constantly 0, then we don't do anything, because then we just, well, we output 0, which is our on the target qubit, which is anyway the case. The nth qubit will just output 0. Well, if the output is 1, we flip the nth qubit, the last one, and then we get, well, we output 1 basically in the end. Okay, and then, so this is our function that defines the oracle. But now it's a function and it's a big quantum circuit. And ideally we want it to be an oracle. So we want it to be, we don't want to see what's in there. We just want it to be one function. So we want to create a gate out of that. That just appears if I then later on display the quantum circuit, it should just appear as one big block that has the name oracle. So it will have the name oracle and it will be just a gate that I can call. And this oracle gate is what I return from my function. Then so let's run this line as well. Then the next thing we want to, now that we've defined our oracle, we can actually put everything together and define the full algorithm, the Deutsch-Jozsa algorithm. Here I again give two variables. The first one is n for the number of qubits. The second one is the case. And here I actually make something that I initialize the case with to be random. And random I will here define later. Which means that if I call this function and I need to give n as an input, I need to give the number of qubits. But if I don't put a case, it will automatically be random. I can still put another case like constant or balanced, but I can also just put nothing and then it's going to be random. So in this algorithm, we start, well, the full algorithm, as you remember, maybe, hopefully, we will create a quantum circuit. Again, we need n+1 qubits. But now we also give a second number here. And the second number is the number of classical bits. So we have n+1 qubits and n classical bits. The n classical bits are needed for the readout later. So because if I do a measurement, then I get classical outputs that are as readout, the ones that we actually observe and that we use then. And these are stored in my classical bits. That's why I create both of that. And now I have another for loop. But you remember that in the beginning, what we do, we apply a Hadamard gate on all of our n qubits. So for qubit in range n, we apply a Hadamard gate. A Hadamard gate is just by the name of the circuit, .h, and then the index of the qubit, which is the one that runs from 0 to n-1 now. Then we also need to set up the output qubit. The output qubit, the last one, that's the one where I told you, okay, it's our auxiliary qubit. And the auxiliary qubit is in the minus state in the beginning. So we can, for example, go there by first applying an X gate and then a Hadamard gate. That way we will end in the minus state, which is the one that we need before we apply the oracle. Now I've created the case random. So let's see for the case, if the case is random, I didn't specify what it means now. And if I want to call my function, I need to tell the function whether it's constant or balanced. I don't have any other options there. So if the case is random, what I want is I just randomly want to choose either constant or balanced. So what I do is I create a random variable that I call random, which is an integer, one out of two integers, so either 0 or 1. If it is 0, I say that my case is constant. If it's 1, my case is balanced. That's it. And then I can actually call the oracle. just the name, Deutsche Rosa Oracle, that's the name that we defined here. The case is now the case, whatever I gave it before, so it can either be a specific case that I set here. If I put balanced or constant here, that would be the case. If I didn't put anything, then it will be the random case, which is also then constant or balanced. And now this oracle gives me another quantum circuit, but I've already created the Deutsche Rosa circuit. And now I've created the oracle, which is another circuit. And now I need to append these two circuits to each other. So I have the Deutsche Rosa circuit, and I just do append oracle, and then all n+1 qubits that I have. Now I stick them together. But then in the end, we of course need again to apply a Hadamard gate to all of our n qubits. So we say for I in range n, for the first n qubits, we again apply a Hadamard gate. And then we apply measurement. And here, this means that we measure the ith qubit and put it on the classical. The outcome will then be stored in the ith classical bit. And so we do I. And we return the circuit. Good, so let's see how it looks like. We can specify some number of qubits. For example, let's choose n equal to 4. And then our circuit is just running this function Deutsche Rosa algorithm. Gives us the circuit, and we can say circuit.draw, and then it will be drawn. And here we go. We can see we have our 4 qubits, the ones that we actually run this algorithm on, basically. Then the oracle, and then again Hadamard gates, and then the measurement. This is the Deutsche Rosa algorithm. And then on qubit 4, that's our auxiliary qubit, where we first prepare the minus state, and then it's needed for the oracle, right? And then in the end, it will also return the minus state again. But that's the one that we don't care about, so we're also not going to measure it. So, and by the way, also you can see here this oracle, it's now just a box, just says oracle. It doesn't say what it does. So now that I didn't specify a case, we got a random case, and we cannot see whether it was actually constant or balanced. Good, but, well, of course, we also want to simulate it and then later run it on the actual device. So let's first choose a backend. The backend is the device that we want to run it on, or in this case, we actually can choose the simulator. Then we specify a number of shots, which, well, in the case of the Deutsche Rosa algorithm, it doesn't make a difference because now we're not considering any noise. If we run it on the simulator, but later on when we run it on the actual device, it will be important. And in this case, we only get, ideally, only one output. So then we create the circuit, which is given by running the function Deutsche Rosa algorithm. Then we execute. So you just put execute and then the circuit that you want to run, the backend that you specified, and the number of shots. Dot result. Then we get the results. And the results would be a lot of different results, but what we're actually interested in for now is just the counts. So we can do results.get counts. Then we'll get all the different counts for the different statistics, which, while using the simulator on the Deutsche Rosa and running Deutsche Rosa's algorithm, we only get one different output, but it might be more, it could be more distributed, especially when we look at the actual hardware. And then we plot the histogram. Let's do that. Oh, and we see we have 100% probability to measure the state 1111. Okay, that tells us that in this case, our oracle was balanced. Because we know that if it's constant, we would get 0, 0, 0, only the 0-bit string. If we get anything else, it will be balanced. The reason we got now the balanced one, that we get now 1111, is just by the way we constructed the oracle. So the way we constructed it was with all the CNOT gates. If we did something else, like just making it dependent on one specific output qubit, then it would be very different. It could be very different. So yeah, in this case, we will just get this as output. Importantly, we're not getting just zeros. So we can run it a couple of times. Or actually, we could also just say here, specify a case. The k we want it to be constant. And now you see if we say it's constant, then we'll get the 0-bit string. But yeah, simulator is of course nice to see that everything we like programmed works the way it's supposed to work. But of course, we're interested in also running it on the actual hardware. So for that, we want to choose a backend. And there are a lot of different backends. So actually, if you go to, do that again, quantum-computing.ibm.com here, and we go, here we can see, if we log in, the IBM Quantum services. I can go on view all. So now we're gonna run this line, and we will see what our least busy backend is. So the least busy backend in this case now is the IBM QX2. Okay, so now we can just run this line. And we will see, okay, the least busy backend is the IBM Melbourne device. And we can see here with this line here, Qiskit Job Watcher, this window here pops up. And we can now see where in the queue we are. So now I'm in the queue at position 1. And so yeah, my job is queued. And this is my job ID, which is important if I later on want to go back to that job, I need this job ID. Then let me quickly show you here what I also did. So we created the circuit, and then we executed that circuit, where here backend now, of course, is my, well, in this case, the Melbourne device. Number of shots is still 1024, which I defined earlier. And now I've added something called optimization level, where it shows 3, which is the highest. And this is good because, for example, it chooses the best qubits that the ideal map of qubits that we can have. So if I go back to my devices, let's look at one of the devices. We can see they have, well, this is the connectivity map. And if I'm now choosing 5 different qubits of those, well, it would be stupid to choose qubit 0 and 12 and 26 because they are not connected at all. What I rather want to do is I want to choose some qubits that are nicely connected, where also maybe the errors are rather small compared to them, because if I don't need all of them, I can just choose the best ones. Plus, I want to align them in a way that, in my case now, for the oracle that is balanced, we apply a lot of CNOT gates. And if I apply a CNOT gate between qubit 4 and 12, then I need to swap with 7 and 10 to actually apply it. So that takes more gates, and that will lead to more noise. So in the end, it would be better if I choose 7, for example, to be the middle qubit, and then apply the CNOT gates with 4, 6, and 10, just as an example. So what the optimization level does, it also cancels, like, or tries to simplify the circuit, but then it also chooses a good map on which we can run it. So let's see. Oh, we see the job has successfully run. Now we can look at the results, get the counts, and again plot the answer. And you will see that this is actually now has a very different distribution. So it's not 100% in the 000 state, but it is actually, it has like around 70% here to give me the output the 0-bit string, and then some noise here. Or just see, for example, it seems like the qubit here, the second one in the bit string, seems to be a bit more noisy because that's the one that flips here, and that actually also flips here. So it seems like that one is less stable than the other ones. As I didn't know before how fast the jobs would run, I was actually running other jobs before as well, just to show you that. And I ran it on the Belay device, or that was at that point the least busy one. And let me just show you how the jobs looked here. So this device has a much has a much better is better regarding to noise. So if we look at all the devices here, we can, for example, see the quantum volume, and we can see the Belay device as 16, and the Melbourne device has only 8. So it wasn't even the best one, but still you can see maybe also the qubits that were chosen were in the end better. So here, when I run it on the Belay device, we actually got 97% to a chance to get the 0-bit string. But this is for the constant case. And then, of course, there's also the balanced case. Let me show you the plot for the balanced case. Here we can clearly identify what the result should be. The result should be the 1-bit string. But we can also see that the chance to measure that string is not even 50%. Now you might wonder why on the same device we get 97% for one case and not even 50% for the other case. And that's because of the way that we implemented the oracle. When you think about what we did for the oracle, in the case where it's constant, it either doesn't do anything or it just at most applies some bit flips. But this can be done very fast and very efficient, and it's just single qubit gates at most. So there's no entanglement created, and you can do that very fast and without a lot of noise. You have a very high fidelity in the end to measure the correct state. While in the case where we have the balanced oracle, we have to apply a lot of CNOT gates between the different qubits, and not all of them are even connected, because given any connectivity map, it's never the case that many qubits are connected, that you could just apply the CNOT between each of them. So you have even more gates than just the CNOT gates that we need for the oracle. And then this leads to a bigger depth, and then, well, since qubits are not stable forever, but have some coherence time, this will at some point lead to more and more noise, and that's why we have here so much noise. And this is also why you can see that it's important that we do a lot of shots. Let's say if we only did one shot, the chance would not even be 50% that we actually get the correct result, but it might just be any other result. If, however, we'll do the 1024 shots, or we can actually do even more, we can do up to 8192, we get the whole distribution, and we can then clearly identify what the result that we wanted is. Okay, I hope you learned a bit about the implementation of the Deutsch-Jozsa algorithm. And then in the next step, we will talk about Grover's algorithm. Okay, so let us now continue with the implementation of the Grover algorithm. As before, we start by doing a bunch of imports. So we first import NumPy, and then we import a lot of Qiskit functions that we need to create our quantum circuit and plotting the histogram. Then we, of course, also need to load our IBM Quantum account. And yeah, we just run the typical imports. And then we get to the definition of our different oracles. We'll start with the phase oracle, which depends on n, the number of qubits. Then the indices to mark, which will be an array where I can just give either one, but also a couple of different indices, which are the marked elements, the ones that Grover's algorithm is looking for. And then also we can give it a name. By default, I just call it oracle. As always, we start by creating a quantum circuit on n qubits and with the given name. Now, this time, unlike for the Deutsch-Jozsa algorithm, this time we will not decompose our phase oracle into all the different gates, but what we will actually do is we will give it a matrix and then convert this matrix into a unitary, and then Qiskit will automatically find a good decomposition that implements this unitary. So we want to create this oracle matrix, and we start by setting it to identity on 2 to the n qubits, on n qubits, or 2 to the n times 2 to the n matrix. So we have ones, it means that we have ones on all the diagonal elements, and then everything else is going to be 0. However, now this would do nothing. Identity matrix is just doing nothing at all to our qubits. But what we want is we want to get, as the name suggests, for the face oracle, we want to get a face, and we want to get this face to all our marked elements. So we do a for loop over the indices that we want to mark. And for each of them, we take the corresponding diagonal element in the matrix and replace the 1 then by a -1. This way, we just get the -1, the face, the -1 face to all the elements that we need it for. And then there comes the point where we need to convert this matrix as a unitary into an operator and append that to our quantum circuit, which we can do with this line on the n qubits, and then we return the quantum circuit. Then the next stage, and the next definition that we do is what we call a diffuser. And I call it a diffuser because that's what it's called in the Qiskit textbook. I'm sure you've all heard about the Qiskit textbook, and well, so if you ever want to look something up, any topic that you want, I can highly recommend it. But so in particular, also there's also a chapter on Grover's algorithm, and there they call the part that I called V here, they call the diffuser. So the Hadamard gates, UF0 and Hadamard gates, is a diffuser. That's why I gave it the name here and called the function diffuser. As you can see here, what in the notes from yesterday, what we discussed when we discussed the algorithm, the diffuser consists of first applying Hadamard gates to all n qubits. So we'll just do that here with QC range n. Then we append this oracle UF0, and UF0 is basically the same as UF, but just that it does not depend on the marked elements. But the only one where it differs is the 0 element, so the element which is the 0-bit string, which has just zeros. And this always corresponds to element 0. That's why we append the face oracle with the marked element being just 0, and then on all n qubits. And then we have another n Hadamard gates on each, so a Hadamard gate on each qubit. And we return this. This gives us then the diffuser. And now we can combine this into Grover's algorithm. So building the whole circuit. As before, we first create a quantum circuit on n qubits. And again, this time we need the n classical bits, because in the end we want to do a measurement and we need to store the measurement result somewhere. So that's why we need n bits for the measurement. And then we actually define R. Remember, R is the number of rounds. And so it tells us how many times we need to run both here you see the UF and the diffuser. We need to run it both R times, repeating it R times until we get so that in this plot here, we go all the way up to our winning element, or one of the winning elements. So R, as defined in the notes, equals pi over, or let's just look at the general version actually for multiple marked elements. So it just corresponds to pi over 4 times arcsine of square root of m over n minus 1/2, which is what I put in here. And then of course in general this is not a natural number, but we need it to be a natural number, so we're rounding it. Then we have an integer in the end. And we can also print, just to get this information, how many qubits we have, what is our marked basis state, and what are the number of rounds. Then, all in the algorithm, as you can see, it starts by creating the superposition state S, which means applying Hadamard gates to all n qubits, which is what we're doing here. Then we have R times our face oracle and the diffuser, which we just defined before, and we just append them. And here this is just a dummy index, which runs over from 0 to R minus 1. And in the end, we end at the measurement of the n qubits, stored in the n classical bits, and we return this quantum circuit. So we can run this line. And let's just look what this quantum circuit looks like if we have, for example, 5 qubits. And then for x, for the marked element, we choose a random integer that is one of the 2 to the n different numbers. And this will be our marked element that we then put into Grover, and then we draw the quantum circuit. And this is what it looks like. So we can see we have 5 qubits. We have the basis state 24, which is the one that got marked in this case. And we have 4 rounds. So we have Hadamard gates and then 4 rounds of oracle diffuser, and so on. And then the measurements in the end. Great, so let's run it on the simulator and see what we will get. So I choose the simulator as my backend. And then I execute the quantum circuit that I just defined using 10,000 shots. You will see in a second why I'm choosing 10,000. And I get the counts and plot them in a histogram. So here we can see our results. And as you may notice, this number here, 11000, is just the binary representation of 24, which was our marked element. So with a 99.9% probability, we actually measure the correct element. But then we do have some small values here as well, which is, by the way, the reason why I chose 10,000, because you can see actually we got, if I output the counts, we get 9,993 counts gave the correct result, the marked element, and then we have a very few others. So if I only had chosen 1,000 shots, we might have just got probability 1 to measure this result. I just wanted to show you that there's also small probabilities. I wanted to show you that there's also small probabilities to measure the other elements. And now you might wonder why that comes from, because the obvious answer would be noise, but no, actually we cannot have any noise here because we're using the simulator and we're not like modeling any noise or something. So this is really no noise. But as you may recall from yesterday, if we turn every time by an angle of theta, in the end we might not exactly reach W, but we might go a bit below or a bit too far. And so we said this R should be ideally some number that we defined here, but in practice then we have to round it, of course. So if I plot here what the R would ideally need to be, ideally we would get 3.92. But well, we chose it then to be 4 because it was the closest that we could round to. And 3.92 is already pretty close to 4, which is why we have still a very, very high probability to get the right result. If we only had 3.5, for example, the probability here would be much smaller. Though still then we can upper bound the error with this 1 minus 1 over 2 to the n. But yeah, so in this case, you can see it would be 3.92 and we got 4. We just have some small probabilities to measure other states, and this is really normal. It's not due to noise, but just due to the nature of our algorithm that we can also measure other values. But now you might wonder, okay, what happens actually if I only run it once, if I chose R just equal to 1 instead of 4? So let's look at it. I defined a function where I'm just going roundwise, and then I plot the counts after the first round. And this is what you would get. So actually you can already identify the element that we're looking for. However, it would only be 25% chance to measure the correct one. And this would look like a lot of noise. And now if we would run it on an actual device where we would have even more noise, that might be much worse. So, well, we better run it multiple times. And here you can see what happens. So after the first round, we get the blue plot. After choosing, when we choose R equal to 2, when we do 2 rounds, then we have the pink one, then the purple one, and after 4 rounds, we have the orange one, which is almost 1, like these 99.9 that we saw before. So yeah, it is recommended to still choose the R optimal to then get a chance as high as possible to get the correct result. But of course, because if we look here at this plot, we're getting closer and closer to the element, and we always have some, so we're increasing our chances to get the right element. But okay, now that we've run it on the simulator, let's see how it looks like if we run it on an actual device, on the hardware. For that, I would choose only n equal to 3, because, well, the fewer qubits, the better chances that we see something useful. Then I choose x and y to be 2 random integers And here I'm just saying that they shouldn't be the same. I want to have two different integers, two different marked elements. So then these are my marked elements that I put into Grover. So now we're actually not like before where we had only one element. Now we will have two elements. Then I can again choose the least busy device. Have the job watcher so that we can see where in the queue our job is. As shots, I just choose 1024 now. And then we'll execute it still with optimization level 3 so that hopefully the best qubits are going to be chosen. And I print the job ID so that later on I can check on that job again. So we see here we have 3 qubits, basis state 0 and 2 are the ones that are marked in this case, and it's just one round. And the least busy backend that was chosen now is the Bilem device. And we can see it's queued, but so I've actually already run it before. That was on the Bogota device earlier today. So let me show you the answer here. So in this case, we had also 2 marked elements, and the 2 marked elements were actually 0 and 4. And you can indeed clearly identify them. You can see here 0 and 4 are the 2 that have the highest peaks. However, you can also see that there's quite some noise. So you can see that, well, there's also like all the other elements also have some probability. But yeah, in this case, it's still visible which ones the ones are that we wanted. But yeah, you cannot run it. So far, it's maybe not too good to run it on too many qubits, but hopefully once the errors decrease, we can run it on more and more and more qubits. Okay, I hope you get an idea now of how to run Grover's algorithm. There's actually also a library that you can use, Aqua, with Aqua. It's just, so there you can do these, for example, satisfiability problems, which is what I mentioned when I introduced Grover's algorithm, where you have some functions that you have some conditions that need to be satisfied, and then you're trying to find combinations of, for example, bit strings that satisfy all these, all the different conditions. And for that, you could easily just write your problem as a satisfiability problem and then give it to the Aqua library, and then it will solve it for you. But yeah, that's for another time. Now I hope you'll enjoy the exercises and the future lectures.